work, you can find the batch version in a link on the same website as freq-ci. Okay, so here is a screenshot of the function that writes the freq-ci input file. As I summarized earlier, the approach here is to read through the input file line by line, look for keywords or other strings that indicate where a particular parameter is located, change the value of that parameter, and then move on to the next line. The random normal and the random uniform functions are supplied through the NumPy computing library. In most cases, the script uses the numbers that it reads from the original input file, or template, really, and simply adds some random noise to it using this applied standard deviation for normal distributions or an encompassing range of values for the uniform distributions. The other requirement for this script, of course, is a capability to read freq-ci's output file for each Monte Carlo trial so that the results can be somehow tabulated. For this example application, each individual trial is really a simulated titration with sulfuric acid. The results are written by freq-ci to a selected output file using the selected output keyword block. Because selected output files are written as tab delimited text files, it is simple to import them as data frames using the pandas data analysis library for Python. After each trial, the resultant data frame is imported and returned to the for loop in the main function, where it is appended onto a master data frame that maintains a running summary, if you will, of all of the Monte Carlo results. Once the Monte Carlo trials are finished running, you can use a plotting library such as matplotlib to display the results, comparing the trial runs with actual measurements, for example. Here, the blue symbols represent data measured in monitoring wells at this particular site that was subject to the study that's discussed in Module 5. And this basically indicates a few things. Here, the blue symbols represent relationships between nickel and sulfate and copper and sulfate, for example. The red dots show the corresponding results of individual Monte Carlo trials. I believe there are some 500 shown here based on the posited model parameter distributions that I had mentioned in the previous slides. Here's a more complete look at the results for this example with various trace metal concentrations and pH compared with sulfate. Both the horizontal and the vertical axes use log scales. Again, this analysis is a scripting demonstration. It's not really any kind of a formal analysis of what's really going on with the groundwater quality at the site. Nonetheless, you can see some patterns both in the field data and in the Monte Carlo simulation results. For the most part, the measured metal concentrations are positively correlated with sulfate, which makes sense if sulfuric acid releases have lowered the aquifer pH. We actually see this directly in the pH versus sulfate graph. There's still a fair bit of scatter in the observational data. The Monte Carlo results indicate similar trends data in some cases, such as with respect to aluminum and chromium, but exhibit sort of poorer matches to the data in other cases, such as with respect to nickel. Perhaps the positive model parameter distributions are off for some of these, or other components of the model may be wrong, such as the assumption of chemical equilibrium, or that the aquifer mineralogy is homogeneous. So all of this provides some clues and some insights in terms of what's going on with the data at the site, and basically provides an opportunity to dig into things a bit further, perhaps revisit the model, collect additional data, and so forth. Okay, so let's shift gears here, and we'll start talking about our second example, which is a fast application. And it's a bit more conceptually challenging than the example we just covered. This is also based on a real consulting problem, but I've made some changes to its definition to streamline things a bit. So a little background first. food and beverage industry operations involve disposal of significant volumes of processed wastewater. Oftentimes, processed wastewater consists of rinsate from storage tanks, tillage waste, and a variety of other sources. The key is that while such wastewater typically doesn't contain toxic or otherwise directly harmful substances, there are often large concentrations of organic carbon and organic nitrogen present. Bear in mind that these substances can oxidize and therefore affect the underlying groundwater chemistry if released. In California, where I live, operators of these facilities can obtain permits to dispose of food and beverage production processed wastewater on the land surface, provided that the operator can demonstrate minimal adverse environmental impacts to the underlying groundwater. So consider a situation where a significant unsaturated zone exists beneath the release location. A slow discharge of processed wastewater will percolate slowly through the vadose zone, with organic nitrogen eventually oxidizing to nitrate, which is an undesirable groundwater constituent at elevated concentrations. On the other hand, faster discharge rates reduce the residence time in the vadose zone and increase water saturation, thus reducing the nitrate production. In addition, organic carbon that escapes oxidation, which is more likely in this scenario, is available to convert any nitrate that is produced into molecular nitrogen via denitrification. However, the flip side of this scenario, again, this would be a rapid release of wastewater, is that you're having somewhat chemically reduced water that still contains dissolved organic matter entering groundwater where undesirable conditions such as iron or sulfate reduction may occur that could impact drinking water taste and odor if somebody is using that groundwater for water supply. Let's think about how to go about setting up this process wastewater disposal problem as a simulation. Before we get into the details, I want to stress that this is a fairly schematic model that we're really using here. It's intended to show how to put together this type of simulation rather than focusing on the validity of the various assumptions employed. So let's summarize the key issues. This particular system will be modeled as a one-dimensional flow problem, testing the impacts of different process wastewater discharge rates on water quality. Dissolved organic carbon represented stoichiometrically as CH2O, and dissolved organic nitrogen, which is represented by the chemical formula for urea as a surrogate, drive key reactions in this system. Unsaturated flow, as described by the Richards equation, determines residence time in the vadose zone, as well as the distribution of water saturation. More on that in a bit. Reaction kinetics, specifically the rates of oxidation of organic carbon and organic nitrogen, are an essential component of the problem and must be considered in the chemistry input file setup. For this particular course, this will provide an example of how to handle specifying kinetic constraints for reactions that occur purely in the aqueous phase. Again, the takeaway message here is how to set something up rather than the specific rate laws that will be used for this example. As a first step in simulating this problem, let's first consider the unsaturated flow component. Once again, FAST only really considers fully saturated groundwater flow, where whether it's transient or under steady state conditions. It does, however, allow the user to specify spatial variability in both hydraulic conductivity as well as porosity. So this suggests a possible strategy. The first item to do is to solve the Richards equation, and we would do this outside of FAST using an appropriate tool or model. As a reminder, for unsaturated flow, note the equations shown on the right. Equation 1, the Richards equation at steady state, reminds us that the pore water fluxes through an unsaturated porous medium are proportional to the saturated hydraulic conductivity multiplied by the relative permeability. The relative permeability, in turn, is a function of the fluid pressure potential as shown by equation 2. And finally, the water saturation of the porous medium is also a function of the fluid pressure potential, shown by equation 3. At steady state, with the Richards equation solved for a particular problem with its own porous medium properties and boundary conditions, the product of the relative permeability and the intrinsic saturated hydraulic conductivity can be thought of as an effective hydraulic conductivity. This quantity can be exported from whatever model is used to solve the Richards equation and saved as an array in an external file. Similarly, the product of the water saturation and the porosity, otherwise known as the moisture content, can also be saved as an array. This is clearly the water-filled porosity, and it will impact the rate of pore water movement and therefore the residence time in the unsaturated zone. In addition, the diffusion of atmospheric oxygen through the unsaturated zone is strongly influenced by water saturation. If we assume, as a simplifying first approximation, that gas phase diffusion will occur below some threshold water saturation, then this calculation directly impacts the chemistry side of the FAST model setup. Now let's have a look at setting up a one-dimensional steady-state solver for the Richards equation in Python that will be used to inform our FAST model. There are a number of ways to approach this problem, but a convenient one that I have found is to use a canned ordinary differential equation solver, which is supplied by the SciPy scientific computing library. The setup is outlined here, and we'll look at the actual Python script to do this in a bit. First, we want to rewrite the expression for the unsaturated water flux of water as an ordinary differential equation so that we are looking at the derivative of the fluid pressure potential with respect to elevation. Next, recall that the total fluid potential is just the sum of the pressure and the elevation terms, and that the pressure term is a negative quantity for unsaturated conditions. And finally, with some algebraic rearrangement, we arrive at an ordinary differential equation for the relationship between fluid potential and elevation. This is now in the form that we need to deploy SciPy's ordinary differential equation solver. So a Python script to solve the Richards equation in this manner is included in the course materials, and I'll also send out a copy of it after today's webinar. I'm just going to step you through some of the key features here, and you're certainly free to ask questions if you'd like using the chat feature. We can discuss that at the end of the webinar today. So a few items to note. A few libraries need to be imported as indicated in the upper left of this screenshot. These include the ODE, Ordinary Differential Equation Integrator from SciPy, as well as the interpolation library. We need the latter to interpolate values of unsaturated hydraulic properties for the column as a function of elevation, which is specified as an external file. A class is defined here, which handles the unsaturated soil hydraulic properties and also defines the Richards equation. When the soil object is first created, an external delimited text file is read that contains saturated hydraulic conductivity values as well as various empirical expressions for relative permeability and saturation as a function of elevation. The interpolation function within the column. The first three functions or methods in object-oriented programming parlance define various unsaturated soil hydraulic properties as a function of fluid pressure potential, directly implementing the equations that were spelled out a couple of slides back. Finally, the Richards method expresses the ordinary differential equation for the Richards equation as developed on the previous slide. Continuing on here, the unsat flow function is the main function of the script. First, it sets up the soil class, which we just went over on the previous slide. Next, it defines the vertical grid for the simulation. It then calls the differential equation solver. Again, the Richards method in the soil class provides the actual equation Size 0 is just the boundary condition at the water table, and Q is the applied process wastewater application rate. And we'll see more on that